Shock. Definition. Shock is a life-threatening condition of circulatory failure, causing inadequate oxygen delivery to meet cellular metabolic needs and oxygen consumption requirements, producing cellular and tissue hypoxia. It may be initially reversible, but becomes irreversible if not treated, leading to multi-organ failure and death. Pathophysiology of shock. Regardless of etiology, the initial physiologic responses in shock are driven by tissue hypoperfusion and the developing cellular energy deficit. Pathways leading to decreased tissue perfusion and shock. The pathways leading to decreased tissue perfusion and shock involve various cellular effects and triggers. Decreased tissue perfusion can result directly from hemorrhage, cardiac failure, or neurologic injury. Decreased tissue perfusion and cellular injury can then result in immune and inflammatory responses. Cellular effects leading to decreased tissue perfusion and shock can result from various factors that disrupt the normal equilibrium between the host and microbes, leading to an inflammatory response and cellular injury. Disruptions in the host microbe equilibrium cause a release of bacterial products like lipopolysaccharide. Severe trauma can cause tissue injury. Damage-associated molecular patterns, high mobility group Box1, and heparin sulfate are examples of damage-associated molecular patterns released during tissue injury. These factors activate pattern recognition receptors, like toll-like receptors and receptors for advanced glycation end products. Activation of these receptors can initiate immune and inflammatory responses, leading to decreased tissue perfusion and the potential development of shock. The vicious cycle of shock. The vicious cycle of shock is a complex and self-perpetuating process that occurs when the body's compensatory mechanisms to maintain perfusion fail, leading to a downward spiral of worsening conditions. It involves multiple interrelated stages and symptoms, including cellular, microvascular, and systemic responses. Cellular stage. As perfusion to the tissues is decreased, cells are deprived of oxygen and must switch from aerobic to anaerobic metabolism. The product of anaerobic respiration is not carbon dioxide, but lactic acid. Accumulation of lactic acid in the blood produces systemic metabolic acidosis. As glucose within cells is exhausted, anaerobic respiration ceases, and there is a failure of sodium-potassium pumps in the cell membrane and intracellular organelles. Intracellular lysosomes release autodigestive enzymes and cell lysis ensues. Intracellular contents, including potassium, are released into the bloodstream. Microvascular stage. Hypoxia and acidosis activate complement and prime neutrophils, resulting in the generation of oxygen-free radicals and cytokine release. These mechanisms lead to injury of the capillary endothelial cells. These, in turn, further activate the immune and coagulation systems. Damaged endothelium loses its integrity and becomes leaky, resulting in tysodemia, exacerbating cellular hypoxia. Systemic stage. The microvascular dysfunction triggers a systemic response involving multiple organ systems. Cardiovascular. As preload and afterload decrease, there is a compensatory baroreceptor response, resulting in increased sympathetic activity and release of catecholamines into the circulation. This results in tachycardia and systemic vasoconstriction, except in sepsis. Respiratory. The metabolic acidosis and increased sympathetic response result in an increased respiratory rate and minute ventilation. This, in turn, increases the excretion of carbon dioxide, resulting in compensatory respiratory alkalosis. Renal system. Decreased perfusion pressure in the kidney leads to reduced filtration at the glomerulus and a decreased urine output. The renin-angiotensin-aldosterone axis is stimulated, resulting in further vasoconstriction and increased sodium and water reabsorption by the kidney. Endocrine system. Vasopressin, an antidiuretic hormone, is released from the hypothalamus and responds to decreased preload, resulting in vasoconstriction and resorption of water in the renal collecting system. Cortisol is also released from the adrenal cortex, resulting in sodium and water resorption and sensitizing cells to catecholamines. Ischemia Reperfusion syndrome. During the period of systemic hypoperfusion, cellular and organ damage progresses due to the direct effects of tissue hypoxia and local activation of inflammation. When the normal circulation returns, the cellular and humoral elements activated by the hypoxia, complement, neutrophils, microvascular thrombi, are flushed back into the circulation. They cause further endothelial injury to organs, such as the lungs and the kidneys. This leads to acute lung injury, acute renal injury, multiple organ failure, and death. Prevention of reperfusion injury is by reducing the extent and duration of tissue hypoperfusion. That's all for the video. We'll see you next time.